Impressive. That was very, very impressive. Cool. All right, good. We can go live now.
So you can tell me when I should share the screen, right?
Okay, we'll do. Yep. Perfect. Hello, everyone. We are live. We are in live stream number 88 and very, very excited about today's live stream. But before we get into that, just want to make a couple of announcements. As you may well know, we will be participating in KubeCon on October 12th with our co-located event about data on Kubernetes. So you can register here. We already got over 500 people who are registered. The schedule for that, the final schedule will be coming out tomorrow. So you can check that out too, to see all the different talks that are going to be happening, when they're going to be happening, what they're about. But we're not here to talk about that today. We're here to talk about something a little bit more serious, which is security. We have had talks about security. We've had talks about Open Policy Agent. We've had talks about Kyverno. We've had talks about a couple of different things related to IBM's approach to security on Kubernetes. But we have not really, I wouldn't say we've touched on this subject as much as we need to. And something that comes up a lot, right? Is security a day 3 thing, or maybe a day 0 or a day -1? How soon should security become a factor? How can it be approached? What are the risks, but also what are the best practices? We also had a nice live stream a couple of weeks ago talking about misconfigurations that can cause problems. So maybe that's something we can also touch on today. But I'm not the security expert. Our wonderful guest, Leonid Sandler from ARMO Sec, who's joining us today from Israel. Leonid, very, very nice to have you with us today. What can you just give us a little bit of background about you as a cybersecurity expert and also about your role as CTO in ARMO?
Right. Hi. Hello, everybody. Thank you very much for taking your time joining us. So my name is Leonid, and I'm a CTO and co-founder of ARMO Sec. My background goes many years back into software security in the video DRM area. And several years ago, we have founded ARMO and decided to build a product that brings very high security capabilities to the cloud. And with a huge success of Kubernetes, we basically retargeted the product to work with Kubernetes and provide end-to-end security for Kubernetes, covering configuration management, something that sometimes called a posture, and the runtime, which are working together. And I'll explain how it works and how it fits the context of NSA and CISA Kubernetes guidance.
Okay. With this in mind, seeing the transition over time, as you've been working in cybersecurity for a while, what are some of the challenges that regarding cybersecurity that are unique to Kubernetes that maybe we hadn't seen before, or perhaps they're maybe not as unique as they seem? It seems that there's sort of the idea that with great freedom comes great responsibility, and also the need to maybe get some guardrails in there. What's your thoughts on that?
I think it's a little bit of both, or a lot of both, actually. Kubernetes by itself is a very complicated system because it really the orchestration level that has to provide any potentially needed flexibility to run any application in that environment. But by itself, Kubernetes runs in the cloud, which is another orchestration system, giving you VMs, resources, storages, networks, etc. And these two systems basically run one inside of the other. So I would say from the cloud standpoint, Kubernetes is kind of a blind spot of the cloud because cloud has to provide the resources which Kubernetes can use at its disposal in any possible way without any limitations. Kubernetes doesn't like limitations. It can limit you, but it doesn't like to be limited. On the other hand, the different container runtime layer engines and different network plugins and different packages from different cloud vendors create a lot of entropy, create a lot of kind of platform dependent or Kubernetes dependent or cloud dependent problems that any system needs to address to actually be secure at the end of the day.
Very, very good. In this particular case, we were talking earlier a little bit before we got started. ARMOSec very quickly responded to these NSA, guidelines and best practices to harden Kubernetes. You very quickly jumped on that. Were the things that you found there surprising? How did you react to that?
Well, I'm going to talk about this a little bit during the presentation and some demos, but it's a very good question because really these guidelines came in early August. And we were working on other frameworks at the time. We were working on Mitra framework, CIS framework, and looking at other kind of guidelines and the implementations of Kubernetes configuration scanning. And when this document came up, it was clear to us that first of all, it's going to stick because it's really a very profound, very good document with a lot of information. And most importantly, it's not as prescriptive as other guidelines. It gives you a lot of details, it gives you a lot of information, what you need to check, but it also gives you a lot of freedom. And you need to think about this in context of your specific environment. They describe the problem, give you some examples of the solutions, but you take it from there and you actually bring it to the environment that you actually need to protect. And I think that we liked it, and we used everything that we have developed before for other frameworks, pulled them together, compared controls and the infrastructure, and of course developed new things very fast to integrate OPA and Go engine and Kubernetes access interfaces all together to implement this guideline.
All right, very good. That being said, if you would like to share your screen, we can jump right into the presentation. For folks that are attending, remember, you can put your questions in the chat and we'll happily answer them on the go.
Right, so let's start from here. Can you see my screen?
Yeah, looks great.
Yeah, let me also remove this so I'll see the whole screen. Okay, there we go. So we're going to talk about Kubernetes security, or specifically data and secrets in Kubernetes in the context of this NSA and CISA Kubernetes hardening guidelines. So we primarily focus on data because this is the interest of the forum, I understand. And so a few words about this Kubernetes hardening guidance. Okay, as I said, it was released last month. There's a lot of information in there, but a few important things that I wanted to emphasize. The document clearly states that data theft is a traditional primary motivation for data. Okay, and so everything we do eventually intended to protect our data, intended to protect our resources as well. Okay, but primary subject or primary target is the data. So that's what we're going to talk about today and see how we protect that. And also in some other place in the document, when they talk about potential ways of protecting, they also mention encryption, encryption of traffic, encryption of sensitive data at rest. The example of sensitive data is secret, but don't get me wrong, there are many other examples of sensitive data that we want to protect in Kubernetes environment. And I'll talk about how I see data coming to Kubernetes, what are the ways of handling data in Kubernetes, and how that fits into this protection paradigm. So since the document, as I said before, leaves a lot of room for your own thinking, your own understanding or definition of the problem, this is how I summarized it for myself, okay? And I've divided it into 3 groups. First group is what attackers are looking for. We mentioned data as a primary target, but there are other targets which are also very important, and some of them directly related to data. Okay, keys, for example, secrets, as we're going to talk about them today. They're used to protect data. They're used to protect access to certain interfaces or to our systems, and therefore, I think they're on par with the motivation to steal from the attacker's perspective. Resources, the coin miners become very popular, ad bots, and you name it, whatever other included software in our system that sits in there and uses our resources or uses our money, basically. Okay, the other angle for the attackers is damage, which is ransomware and kind of DDoS attacks, etc., or harming user experience. Some like that. I don't, but of course, we need to deal with those as well. And the intellectual property. Okay, intellectual property can be seen as data, but sometimes it's also code. So we need to look at this from both perspectives and understand how we're going to protect all these things, because this is what, in my view, people are looking for when they come to attack our system. And then basically I need to summarize all different ways of breaking in. Again, this particular document talks about insiders and vulnerabilities, etc., and everybody. But if I take also the information that I had from my background before this spec was released and try to summarize them all together and say what are the primary ways or primary methods in very, very high level of breaking into our system, I would say that there are three of them, three groups of them. A misconfiguration, one of them, credential abuse, theft, whatever, another one, and the third one is software vulnerability. I think for the sake of completeness, we would also have to talk about hardware vulnerabilities, but I think for today we can leave them out. So these three methods of breaking in is something that we need to address. And if we see what people do with them, what attackers do with these methods, when they manage to use one of them or few of them together, we can basically see three major attack angles, okay, of our attack methods. One of them is they will use existing software in a way that it was not intended for. So, for example, if you left your S3 bucket open, and somebody will come and just read it. There is no need to change anything. There is no need to corrupt anything. There is no need to intrude. You just can use existing software, but in an appropriate way. The other method would be to change the behavior of existing software, which primarily done by changing its configuration, injecting some wrong config files or requests, etc., which would cause existing software to behave differently and potentially either reveal some information or allow attack to propagate and go to the third point where we basically inject potentially malicious code. Okay, and again, the injection of the code could be by corrupting existing software, something that we know as DLL injection or arbitrary data or fileless malware type of injection, or injection of additional software or launch of existing additional software like remote command execution, which would normally execute in a separate process than the existing one. Okay, so at the end of the day, as you can see, it's always about software. There's always some way of abusing, changing, or misbehaving the software that you have in the system or the attackers bring into the system. And the way I like to describe it for myself or visualize it for myself is to use this 4C model, the very famous cloud cluster container code model, which many different methodologies use, and talk about two dimensions or two vectors of protection that we need to worry about. One of them is bottom up, and kind of infrastructure type of protection, which I call the security of Kubernetes, which requires us to make sure that Kubernetes itself is properly configured, does whatever it needs to do, and collects necessary information, etc. And the other angle is the security in Kubernetes, which is basically security of the application itself, application that we run inside the Kubernetes. And come to think of it, okay, if you've done completely, if you've done a configuration of Kubernetes completely, and absolutely great, it still doesn't guarantee the security because the application itself may still be vulnerable. And the attackers, they don't really care about who is responsible for what kind of attack. There's any weakness in the system on any layer, they will use it, they will go for it, and they will utilize it and break into the system. One important thing or one interesting thing I wanted to point out on this picture is that container level is kind of sits on both sides of this boundary. It's part of the infrastructure on one hand. It's where the Kubernetes configures containers, and container runtime helps Kubernetes to configure processes that run inside the container. And on the application side, it's also part of the application because in many cases we don't build containers by ourselves using whatever guidelines or practices that we set for ourselves. Sometimes we take containers from outside, and those containers come pre-packed with certain needs, with certain expectations. They can run as root or as privileged, or they need some particular access to some resource. Okay, and in some cases, Kubernetes can take care of that and can basically reconfigure them to be in accordance with your best practices. In other cases, it's not possible either because Kubernetes doesn't know how to do that, or because application requires some capability that Kubernetes maybe could take away, but application will not work. So for example, some applications would require to run privileged. We know it's not the best practices to run privileged containers, so we'll always recommend not to do it, but there will always be an application or some of them that will require that capability, and therefore the container will basically be preloaded with application that is expected to have certain privileges, and Kubernetes will not be able to. Okay, so how do we address this? Okay, and I said that there are two areas or two methods of addressing this problem. Okay, one of the methods is configuration, something that we call the least privileged principle. We always need to apply this least privilege principle to make sure that we are giving our containers, our Kubernetes pods, capabilities that they need, and nothing else, nothing more than what they need. And as I said before, they sometimes need more than we would want it to give them, but we have to somehow deal with them. The capabilities, this configuration can be roughly grouped into several areas. For example, authentication and ARMO. We need to know what capabilities we give to our containers through the ARMO. What can they do? They can run in the cluster and that's it, or they can communicate with Kubernetes and ask for certain resources. They can create other pods, or they just, you know, a final application that does only its own job, etc. We also need to configure pod and network security policies. Again, Kubernetes give us a lot of tools to do this: pod security policy, security context, all these privileges and rootless containers, etc. And network also. We have native policies to control network access in Kubernetes, and we need to find a way to use them. However, if you look at the network policies, you'll see that it's very, very difficult to configure because you need to know what exactly happens in your application. And if we talk about really big microservice environment with tens or hundreds of different microservices, it's very, very difficult to know what to configure in those policies. And the policy is kind of rough because if you don't configure anything, then everything is allowed. But if you configure something, then everything is forbidden. And now you have to enable one by one any communication channel, which you have to know about the need of this particular microservice to use.
We got a question.
Sure.
Referring to the previous slide, security boundary slide, shouldn't it include also a reference to persistent volumes, config maps, etc.? How would you define security boundaries for these persistent constructs?
That's a very good question. I'll address it in a few slides down the road, and we'll talk about persistent
awesome.
volumes.
Very good. Thank you.
Yeah, but that's a very good question. Okay. The next part of this configuration part is what we call the inventory and vulnerabilities. We all know what the vulnerabilities scanning is, and we need to have a full inventory of what we are running and actually run the vulnerability software on them to see where we are vulnerable. However, it only gives us a part of the picture because, first of all, not all the vulnerabilities are known, and especially if it's our own application, then nobody's looking for vulnerabilities in there. So we run probably a lot of them in our system. And the second, even if some vulnerability is known, there is not always a patch available, and industry standard today or industry average today for update, in the good cases, update of vulnerable containers is somewhere around 50 days, which is very, very long. We have to understand that hackers only need 5 minutes, okay? And getting from 50 days to 5 minutes is roughly impossible. So we need to figure out how to fill the gap in there. Okay, and then of course we need to make sure that this configuration is tracked and managed all the way from CI/CD to production, because we want to start as early as possible. We want to start seeing containers and YAML definition files as early as possible to figure out how to secure them, how to configure them properly to fix the problems earlier in the pipeline, so that they will not appear crossing or violating the policies when they get to the runtime and slow down the development. Okay, on the runtime side, I would say we need to enforce what's called the zero trust principle, even though I must say that NSA spec doesn't explicitly mention zero trust principle by itself, but it's very, very well-known concept, and the spec does address several things that are normally provided or expected by zero trust principle. So I'll still refer to this as zero trust. Okay. First of all, we need to gather a lot of observability data. Why we need that? First of all, we need to know how to configure network policy. So we need to figure out what who is talking to whom and how we know what to enable and what not to. Okay, and also we need to know what is running in our system. Sometimes we have much more containers in the repository than in the actual production. And if we know that certain vulnerability never used, then a container with certain vulnerability is never used, then we probably don't want to spend our time to go and fix them. Okay, observability data gives us information that helps us to figure out what we do today. Sometimes we know that vulnerable image is not good, but we also need to figure out how to use our resources efficiently and which thing or which capability to implement first. And gathering the deep observability data, allowing us to decide that, to figure out what is actually used, what is exposed to external world, internet world, and what sits somewhere inside and nobody can get access to this anyway. And this is what will help us to prioritize our actions and figure out what we need to do first. And then we come to a protection of the secrets and encryption of data at rest and in transit, which are explicitly mentioned by the NSA guidance. So this is why I said that there's intersection between the zero trust concept and the spec anyway. And last but definitely not least is that we need to protect our software. And the reason I'm saying that is because why are we doing all that? Why are we implementing network policy? Why are we encrypting secrets? Why are we encrypting data? If the software that runs on our system is legitimate, is intact, then who would expose anything? Who would leak anything? Nobody. The only reason we do all that, we implement all these policies, we try to harden our infrastructure, is because we're afraid of malicious software. We know that something will be exploited. We know that something will be brought in from the back door, whatever. But that malicious software will come into the system and will start doing things we don't want it to do. And therefore, we implement all of these hardenings and configurations, etc. But let's address the elephant in the room, right? If we are able to protect the software that runs in our system and continuously verify that that software was not compromised, was not changed, was not complemented or reconfigured, then maybe the motivation to do all other things or the efficiency of doing all other things will give us better protection, will give us another layer of security that we need, because we know that after following all these best practices, people are still getting out. And the last but very important thing to say on this slide is, why do I say 1 + 1 = 3? We have configuration on one hand, and we have runtime capabilities on the other. But the continuous reinforcement of continuous communication between these two elements give us a lot of potential to improve our protection. I'll give you an example. Most of the guidelines, or all of the guidelines for configuration, say if you don't need service account token in the workload, in the container, don't map it in there. Fair enough, right? If you don't need to communicate with Kube API, then why would you map service account token? Fine, I agree with that. However, If I map service account token and never use it, nothing bad will happen. Again, what I'm afraid of, I'm afraid of this particular workload will be compromised and somebody will use that service account token. So now I'm not mapping the service account token. Somebody compromises my workload, sits in there, and nobody knows about this because he did not use service account token. So we have no means, at least at this particular angle, to identify the problem and fix it. So if I have both configuration and the runtime protection at my disposal, I would say, hey, use service account token, create some dummy service account. Nobody cares. Nobody will be able to cause any damage to your system anyway. The service account doesn't go anywhere, but malicious software doesn't know that. So it will take this token and try to use it. And the moment I try to use it, and I have runtime protection capabilities, I will be able to catch it. And I will not only, system will not be harmed, but I will know that somebody is in my system. The same goes for network policy, right? If network policy tells me, don't communicate with this particular namespace or that particular workload. Somebody breaks into my system, try, get rejected. That's it. Nobody knows about this. On the other hand, if I have runtime capabilities, I could say, okay, go there. I will catch you on the way. I will stop you on the way anyway. You will not be able to cause any damage, but I will know that somebody is there and somebody is doing inappropriate thing. So I will know that I need to figure out who is in my system and how to fix it. Okay, this is why these two elements will help each other to work and continuously improve our security posture and our resilience in the runtime. I hope that makes sense. So we come to data in Kubernetes. I've summarized like 4 primary ways of having data volumes in the Kubernetes cluster. Okay, one way is to have container file system, which is probably not suitable for real, dynamic customer data, but there is still some data can be there. Some containers carry configuration files, potentially secrets, etc. With the data in the file system, okay, and sometimes we need to protect it as well. The other one is the node file system. The node file system has to be mapped to the pod, and most of the guidelines, including NSA, will tell you mapping node file system to your pod is not a good idea. And I'll show you a tool in a second that actually identifies that and gives you that warning. However, in some cases, for performance reasons, you actually need this. I know very big services running in the cloud that are using local hard drives, local SSD drives, actually, to provide high throughput, high performance, and they would break this rule. They know what they do, but they still would break this rule. The third way or the third method is to use persistent volumes. Somebody asked about this before, like EBS, for example. Provisioning EBS, I must say, it's fully integrated with Kubernetes. If you do a persistent volume claim, the Kubernetes will go to the cloud vendor automatically and map the volume for you. You have to be very careful with this, not only from the security standpoint, but also from the cost standpoint, because if somebody has a right to create the pod, they can actually go and map a terabyte drive or multiple terabyte drives in the cloud, and you'll pay for it. So and this is one of the methods where, for example, databases may use, or data lakes and other solutions that require significant persistent storage, they would use persistent volume claims. And as I said, there's no permissions required. There's no control. There's no access credentials or something is required to build or to create and attach a persistent volume to your pod in Kubernetes. And the last one is usage of cloud vendor resources. Basically, something that is provided as a platform service in a particular cloud, like database as a service, S3, elastic file system, etc. It's something that requires certain cloud access credentials, with either IAM role or access keys, or something that you actually need to keep and protect in order to get access to these resources from the Kubernetes pod. Okay, all of them, all of these methods would also require RBAC capability to create pods, clearly, but this is not uncommon. So you cannot you cannot create a variation of pod that doesn't go to platform services, or pod that doesn't have rights to create a volume. So I think that RBAC for pod creation is kind of a common denominator across all of them. Now, if we're going to go and protect these volumes using encryption, as NSA recommends, then we will need secrets, and we will need to figure out how to get those secrets and how to use those secrets. Secret by itself doesn't encrypt anything. We need the secret, and we need some encrypting software or some encrypting mechanism to use it to use the secret with in order to encrypt our data in many of these storages. And for that we have by the way, maybe I didn't mention this, but also somebody asked about config maps before Kubernetes secrets. Okay, they are also mapped to pod as volumes, as file systems, which you can use to read the files from. And I think they just basically mapped through the node local disk on the node. Okay. So this is basically the different types of data that we need to protect. And as I said, if we go and protect them using encryption as recommended, we need to figure out where the secrets come from, how those secrets are protected, how they deliver to our pods, and how they used in our pods. Okay, before we go any further with this, I want to show you a demo of the Kubernetes configuration validation tool, which we have developed. This is the Kubescape that you mentioned before. We have released it several weeks ago, and it's actually getting quite a lot of attention on the GitHub. We were trending for a couple of times, and we gathered a lot of stars, which is a very good thing. And I encourage all of you to come and see this tool and try this tool, but most importantly, talk to us. This is the way, the reason we release this tool to open source is we can reach as many people as we can, get the feedback, get the wish list, and figure out how to make it the most usable and most convenient for everybody. Okay, so I'm going to go ahead and show you how that tool works. It's actually very simple. What we need is this is the GitHub with the Kubescape. Okay, if you scroll a little bit down, you'll see the installation command line. It's basically a curl that downloads the script and goes to Bash. Some people say they don't like it, and I understand why. But you can always go and download that Bash file separately, look at what is in there, and then decide to run it, or even take pieces from it and then exercise different pieces manually and download a Kubescape from the repository in the GitHub by yourself. So you don't need to use full automation, but it's important to see how simple that can be done if you actually use one. Okay, what I did now, I've just pasted it into the Cloud Console, and now that's the command line. I'm going to put it here and run it. Okay, let's see what happens. This console goes to my Google Cloud cluster. Okay, take a couple of seconds. Voila, we have the results. Now the results are in two parts. Basically, there's a summarizing table at the end that shows you all the controls that we have run against this cluster. Number of resources in every area. Sometimes resources are pods or deployments. Sometimes are RBAC objects or whatever. So there's different amounts of them. And then you also see how many of them are successful. If you scroll a little bit up, I'm not going to go all of them because it will take a lot of time, and I encourage you to go and see it for yourself. But you can see the details of every control, basically why it failed, what specific Kubernetes objects have failed, and why they failed. Okay, this tool is embeddable into your CI/CD environment. It will return an error if something goes wrong. You can scan the entire cluster. You can also exclude namespaces if you want. As you saw in the command line that I've run, I've excluded kube system namespace because it will give me a bunch of privileged containers in there. And I already know that they should be privileged and there's nothing I can do about them. So I excluded those namespaces. But if you want to target this particular tool to a specific namespace, you can exclude all the others. Maybe we should have an option to include one instead of excluding others. Would be an interesting idea. Okay, but some of the relevant controls that I wanted to show you here in this table are, for example, mapping the host path. All the guidelines I know say this is not such a good idea because mapping host file system would allow a workload to actually go where it's not supposed to go, remain persistent if necessary, or read information from other parts or other elements on the host and potentially cause some damage or maybe steal some valuable information. If you make it completely wide open, you can go as far as stealing a kubelet certificate using this method. So it's not really a good idea, but as I said before, some workloads would need it. So you will get it failed, you probably would want to exclude it. And but you still need to know that you have workloads that are doing this. Okay, unfortunately, containers that we download from public repositories or third-party vendors, they are not always top-notch in terms of their configuration. And sometimes it's better to run this tool and then configure your Kubernetes to actually take certain responsibilities, for example, turn file system to immutable, etc., etc. Now, the other important or interesting thing to look at is the application credentials in the configuration files. Okay, we'll talk about this a little bit more when we talk about the secrets, but it's important to scan all the files and see that there's no suspicious parameters that may potentially be used as password, credentials, access keys, and you name it. There's basically endless possibilities how to call them. And I will always encourage people not to put credentials into configuration files. And later on, I'll explain why Kubernetes secrets is a much better option. Okay, you can see automatic mapping on service account. Again, it's not recommended. Access to host network, access to immutable container file system, as I said, existence of the network policies. In some cases, when policy exists, we know that basically people who defined network policy, they have only enabled what they needed to enable. Otherwise, there's no point to define the policy. So that would kind of give us a hint that somebody was thinking about this and then doing this. So these are the current controls. We have released the new version, actually really probably still releasing a new version, but it will definitely go out in very, very short time. I want to encourage you to go and check it out. That version has additional capabilities. It will allow you to keep the scanning results in the cloud and view them in the chronological way to potentially see what degradations or drifts you have in your environment from one scan to another. It will also allow you to manage exceptions. You will be able to exclude certain objects from scanning and potentially also certain controls, certain checks themselves. And as we go, we're going to add more and more capabilities to the system. And not only I want you to use it, I also want you to give us feedback and ask for what would help you, how you see this, and how would you want to do this. And this product is going to grow. I'll show you later on how it's going to connect to basically the rest of our ARMO product that existed before Kubescape. Okay, so this is about the Kubescape, and back to our presentation. Next thing we want to talk about is secrets in Kubernetes. We said if we want to protect data, we need secrets. We also need other things, but we definitely need secrets. And secret protection or dealing with secrets in Kubernetes is also twofold, just like a security in general. It has to do something with configuration and has to do something with the runtime. Okay, and I divided it into two groups. Okay, first of all, I always recommend to keep secrets in Kubernetes secrets, not in the config files, maps, environment variables, etc. There are two primary reasons for it. And you know, if you look under the hood in Kubernetes, you will see that there is absolutely no difference between handling of Kubernetes secrets and handling of Kubernetes config maps. There are two completely identical mechanisms. They sit in the same etcd database, and they have absolutely the same methods of control. The reason that Kubernetes developers separated secrets from config maps is that you will be able to define different RBAC properties for different users. So you may have users that can access only config maps, and you can have users that can access only secret or secret and config maps. So you can separate on the RBAC level the access capabilities to secrets from other things. This is, first of all, it's good because it goes towards a least privilege principle, but also it's good because it tells the posture scanning tools or configuration scanning tools, what do you want? What is that object? And how do you want to treat it? So when I see a secret, and potentially when I gather this deep observability data that we discussed before, I can actually tell you that you have a secret mapped to certain workload that never used it. So you can unmap it. When I only see the mapping, there's not enough information for me to decide whether it's a right mapping or wrong mapping. But when I gather runtime information, and I know that this is the secret, I can basically give you much better diagnostics and suggest not to use that particular or unmap that particular secret. Okay, a fourth least privilege rule everywhere. Least privilege rule in this particular scenario means if certain workload doesn't need secret, don't map it to. If certain user doesn't need access to secret, don't give them the access rights. Okay. Make sure that etcd is properly configured. Properly configured means at least two things. Okay, it's statically encrypted. Not always you can actually make sure of that. Sometimes cloud vendors hide this information from you. You can only trust that they are doing a good job. The second one is even more important: is who can access etcd. Okay, if etcd is configured properly, it means that only Kube API can communicate with etcd over mutually authenticated TLS channel. And this configuration is actually not part of the etcd itself. It's not part of the config file. It's controlled by the command line parameters of etcd and Kube API. And it's not, again, not always possible to actually see this. So you have to figure out some clever ways on different methods of how different cloud vendors do this to make sure that this is configured properly. But to be honest, cloud vendors do actually pretty good job. Okay, of course, we need to restrict RBAC permissions for secrets, which means that we don't need to, we don't want different roles or different users with different roles to be able to access secrets. And also it's applicable to service accounts. We want to be very careful which service account has access to secrets, not only reading them or writing, or not only writing them, but also reading them or even listing. Okay, it's all, as I said, all goes to the least privilege principle. On the zero trust level, as NSA suggests, we need to encrypt secrets at rest. It's a very good idea, but who's going to decrypt them? And to encrypt them with what? This is the secret, right? We actually put secret away so that it won't be seen. And now we're going to encrypt it with something that we had before. Kind of ambiguous suggestion, right? So I'll show you how ARMO does that. But anyway, I'm comparing. We have done actually pretty extensive webinar on security of the secrets, comparing Kubernetes secrets, cloud vendor KMSs, and third-party systems like Vault. I think it's available, and my colleague Jonathan, who is somewhere here on the call, he will be able to share this information, and you can see what are the differences between all these different methods. Okay, today we're focusing on the Kubernetes secrets, so I will not go to that corner. But still, I suggest to use Kubernetes secrets, and then, of course, on top of that, additional solutions that can protect them, not just at rest, but also in transit and potentially also in use. We have to define very strict access policy for the secrets. But again, who is going to define that policy and who is going to enforce that policy? If some application needs to read the secret, how do we know that this is the application that is supposed to read that secret? How do we identify it? Do we use it by name or by some cluster name, namespace name, and the deployment name? That's probably not very strict identification, because anyone who can create a pod will be able to fake it and basically access the secrets that we don't want to leak out. So we need to figure out how.
Can I ask a question really quickly?
Sure.
Is when we're talking about the stakeholders that are involved in this, is this a platform team? Is this a security team? Are these developers? Is it on a need-to-know basis? Who are the folks that that need first and foremost to understand how this works, and then how does that get also that knowledge shared throughout a larger organization?
Well, I think it really depends on the structure of the organization. Okay, there are some organizations that are DevOps driven, and then of course the knowledge have to come from them, and this is why we basically started to go with this Kubescape tool and talk to DevOps, create this engagement with them, and explain how to take it to the next level. In bigger organizations, I think the motivation and the requirements to do this kind of zero trust functionalities is coming from the top, coming from CISO and security organizations, maybe in some of them from the R&D organizations. But there's no like a one size fits all answer to this. Really different organizations have different methods of handling that. Some of them are required to be compliant with some regulations. Some of them just do it for their own understanding of how security should work, etc.
Okay, got it.
The last point I wanted to mention here before we move on is what is the secret zero? Why we call it the secret zero? Okay, and I kind of already hinted on this before. We need to deliver a secret to application, and the whole reason that we put the secret away initially is because we know that application is not really good at keeping secret, especially when it's not running. Okay, so now application wakes up and has to go somewhere and get that secret. How do we know when the system that keeps that secret? How does it know that application that's asking for it is the right application? Okay, and there are actually two methods of doing this. There's a pull method, like key management system, where you go somewhere and say, give me my secret. Or there's a push method, like Kubernetes secret, that say, if we see pod A going up, we're going to basically push that secret and map a file to that application so it will be able to read it. Okay, but then again, if you look at the threat model and see how much, even if the pod is still called A, it could be a different command line in it. It could be a different container image in it, or corrupted container image in it. So that secret will automatically go to anyone who called himself pod A. Okay, and so when the spec suggests to encrypt secrets at rest, we need to figure out who is going to decrypt them and what key they're going to decrypt it with, and how that key is gotten to that application that we didn't want to have any secrets in the first place. Okay, and we'll talk about this in a minute. So let's go to the next one. Okay. So one important thing to say, we've talked about secrets in Kubernetes, and we'll still talk about this more, but secret lifecycle is much wider than just Kubernetes. It starts much earlier. Secrets are created way before they are loaded into Kubernetes cluster. And when they are created, they go to some backup. I'm not sure there's somebody here who would create a secret and not make a backup of it. They go to some scripts or YAML files or Helm files, and those files go to normal like infrastructure as code type of CI/CD systems or Git or Git, and secrets are there. Secrets are in the clear. So how do we protect them in there? Hacker doesn't care where to steal the secrets from. He will take the most, the easiest way, the most appropriate for him way. He does not going to fight us only in Kubernetes because he's a gentleman. Okay, so we need to figure when we deal with secrets even before they loaded to Kubernetes, we need to figure out how to protect them there. And this is not a simple subject. And then after they loaded to Kubernetes, they also sit in the etcd, either in the clear or etcd is encrypted with some key which sits next to etcd in the config file. So that key would only protect us if somebody breaks into the data center, steals a hard drive, and runs away. Okay, we're not talking about this attack vector at all, right? Nobody knows where our hard drive is among this million hard drives in the center. So how the secrets are protected, and then later on, when workload starts, the secret is pushed into the file and sits there until application decides to read it, or application never decides to read it. But during this entire life cycle, our secret is either in clear or under protection of some different third-party system inside the Git or other source controls. Okay, and this is important to understand before we talk about the protection of the secrets. So in Kubernetes secrets, the secret, as I said, sits in the etcd. For the sake of this discussion, in the clear, because we can only have a programmatic access to it, and if we have some access, then it will be decrypted automatically. When the new pod is launched and that requires that secret, Kube API will pull that from the etcd and push it to kubelet, and kubelet will basically create a file or environment variable, even though I don't recommend using environment variables, but still it's possible. So kubelet will create a file or add it to a container launch command line to create the environment variable. And during this entire process, okay, the secrets are basically not protected. And nobody knows, except for the name of the pod, nobody knows who is actually going to read them. What ARMO does, okay, in this particular angle, in this particular zero trust protection of secrets, is encrypting the secrets. And I will show you the entire life cycle in a second, but important to see that it's going to sit in the etcd encrypted. It's going to be taken by the kubelet, still encrypted, put into the file, which is mapped to the pod, still encrypted. Okay, so probably ask the question, who is going to decrypt it and when? I'll explain this in a second, and I'll also show you how it's done. Okay, but the idea is that through the entire life cycle, the secret is always encrypted. And this is really, to the letter, follows the recommendation of this NSA CISA guidelines, because they really understand what the problem is and how many different potential attack vectors can go and snatch secret from different places during the life cycle. So basically what you would do, you would create a secret and immediately encrypt it. We have a CLI tool, UI tool, whatever you need. From this moment on, that secret can be thrown away on the sideboard, because the moment it's encrypted, nobody can use it, nobody can get it and cause any harm with it. It can go to any backup system, it can go to any source control, it can go to any script, whatever you want. The secret is completely encrypted all the way. When it gets to etcd loaded to Kubernetes, it's still encrypted. So what happened at the end of the day when the secret is being basically mapped back to the application, the kubelet will take it from the etcd, remove base 64, and put on the hard drive. And that's the binary secret that is still encrypted that we put into into the system before. Now, at some point, application will need to read the secret, okay? And the idea here is that the secret will be decrypted only for the process of this application that ARMO has validated. Remember, we talked about the biggest problem in the runtime is how do we protect our application? So here's the point where I explain what we do differently than the other systems. Okay, and this is basically how it's going to be done. We have built a technology that allows us to continuously verify something that we call the DNA of the application during the runtime. So when your container is launched, there's a process or multiple processes that are running inside that. And let's assume that this represents the boundaries of the process. Every process contains executable shared libraries, scripts, configuration files, or config maps if it's Kubernetes, environment variables, command line parameters, etc. What we say is that collectively, all these artifacts, they constitute a unique DNA or unique kind of a signature, if you wish, of the process. There's only one possibility. There's no, just like basically DNA itself. Okay, uniquely identifies the process because everything you need to run that process and distinguish between it and others is in there. If one process is NGINX and another one is MySQL, then it's very simple. The executable will be different. That's it. But if this is two different instances of NGINX or two different instances of MySQL, then all of the executables will be the same. And then you will need to figure out what is different. And the difference will be in the configuration, okay, or environment variables again, or command line parameters. We take all of them into account. If this process is, for example, Python, then everyone will run the same Python, but the difference will be in the scripts. So the idea is to digest all of these elements and create this unique DNA, which allows us to understand what this process is rather than what this process does. And when it goes up in memory and try to read the file, basically the open file, read file, and whatever commands will go through this ARMO guard, which is automatically attached by the Kubernetes to that process without changing anything, without changing containers, without changing command lines or architecture. It's completely transparent. All it does is basically generates this digest, figures out that this process is who it says it is, and only then when it reads the file, it will automatically decrypt it and give it to the application. So application will never know that this particular secret was ever encrypted. And this is done using a unique technology that we've developed, which is a moving target defense technology, which not only make it much stronger, but also reduces a window of opportunity to attack or to reverse engineer the system, because by the time the reverse engineering of this will be done, this element will no longer be interesting, will no longer be applicable, and user will have to start everything over. This system is provided as SaaS or can also run on-prem, but the idea is that it really stands and implements the requirement exactly as it's stated by the spec. We don't change anything in the application, but the secrets and potentially any other data is always encrypted at rest, and it's always delivered only to the valid, validated, and healthy application, which we not only validate at the time of reading, but also continuously validate after that. So for as long as application is running, we continuously validate that it remains healthy during the time it uses that secret in its memory. I hope it makes sense, and I wanted to show you actually how it works. So I'm going to go to a second phase of my demo. Okay, I'm going to use this Google online boutique application, which is a microservice demo from Google running in Kubernetes. Multiple microservices running already in my cluster. You can see them. This circle around them means that we have already generated this DNA and all of it is already enforced. So we can see that all of these workloads are healthy. And by the way, there are other webinars where we have described how exactly to do this. There's a webinar called From Zero to Zero Trust. You can see the entire process, how it's done. It's really a couple of clicks and you're there. There's no need to do any complicated learning periods or anything. So this system is currently running. And what we will do to prove our point is basically we'll behave like the attacker. We will abuse credentials of this cluster and inject malicious or different code into one of these workloads and see what happens. Okay, so we'll use this BI monitor for that. Let's go back to the cluster. We need to reconnect because Google disconnects automatically from time to time. Let's give it a second. Yeah, there we go. So we're going to see what is running in our namespace. These are the pods. We'll see the pod called BI monitor, and we'll go in it. Okay, so we are now running inside the pod. Those of you familiar with Kubernetes know exactly what happened. Okay, and by the way, if you remember this this structure, okay, this runs in the cluster. The BI monitor communicates with the front end, which is the HTTP server. So I'll be able to show you also the protection in transit if we have time. Okay, but for now, let's see what we can do for data at rest. So we have some secrets that are mapped into this BI monitor component. Okay. And this BI is written in Python, so the legitimate application, the application that we have mapped and created DNA for, is Python application with some scripts. So if I'm using this Python application, which, as I said before, it's legitimate, so it can basically run without any problem. Okay, I'm going to read my secrets. Okay, it's a Python script that just read the secret files from the disk, and as you can see, it basically reads them fine. It doesn't even know that these secrets are encrypted. It just takes them, prints them out, and it's okay. Very, very simple script. If somebody wants to know the details and see inside, etc., it will be possible. Please contact us after this, and we'll show you everything that happens inside. Okay, but I also have another application here HexDump, which was not mapped during the observability process, and it was not signed, so it's not part of my DNA. And now I'm going to use this application to read exactly the same file. So, for example, I'll take username. The secrets are mapped into the files, as I said before. One is citizen etc secrets username. Okay, and voila, as you can see, there's no resemblance between what you see here in the hex dump and the secret that you see above, because this secret is encrypted. And other application came to read this. It didn't have the right DNA, it didn't have the right permissions. So obviously the file is mapped. We cannot stop that. Linux allows you to read the file, but ARMO does not allow you to decrypt it because you don't have appropriate DNA. So let's take a password, for example, and see exactly the same thing. You see the password here, you see the password there. Okay, both of them, and system keeps running. There's nothing happening. Okay, we did not stop anything. We did not kind of change anything. Okay. The other thing I may want to show you, we do have a couple of minutes, is how to communicate. Remember, the spec said also encrypt your data in transit, which means during the communication. So this BI monitor communicates with the front end, and again, I'm going to use Python to communicate with the front end. Okay, and you will get some HTML file, because this is what web servers do. They return HTML files. I also have a curl here in the same environment, which was not mapped, doesn't have the right DNA. And I'll also go and communicate with the front. Okay, and we'll see what happened. Voila, it also gets the HTML file. So what happened? What actually happened is we did not define any policy. When in encryption, I said which workload, which DNA can actually use that particular encryption key. In the communication, I did not say that. I only created the signatures and signed all of this workload. So in order to demonstrate this, I need to go back here and say, I want to create a network policy. So let's create a network policy, which we call the basic policy. Let's call it 1. Okay, that policy will be permissive. And the basic policy will say everyone who runs in that cluster. Okay, a cluster called DoK. And the namespace that called hipster, they're now part of the club. Will allow them to communicate with one another, because this is the policy that we want to enforce. Okay, and we'll apply. It takes several seconds. Okay, the policy is now being distributed and delivered to all of the workloads. Okay. Okay, it's on the way. So when it's done, basically the ARMO guard starts automatically enforcing that policy. So if we're gonna go back here, back to our cluster and say, okay, now let's go and communicate with our front end from Python again. It works. And if we go to communicate with the curl, oops, demo effect. Apparently, we still need to wait a little bit longer until that policy is propagated. Okay, but the idea is it's not supposed to work, and at some point it will be rejected. Live demos are always good. Okay, I think this is it for today. If we have some questions, I'll be happy to take them.
Very, very good. We had just some great feedback already in the chat, but I wanted to ask a couple of things. You know, you said in the process of doing this, you interacted a lot with DevOps folks. In terms of what you're doing now with Kubescape, if people want to get involved in the project, what's the best way for them to do so?
Well, first of all, you can contact us directly. You can contact us on GitHub. We're also opening a Slack channel and all the other communication methods. But we have a website, and you can send us email or any information. You can also just engage in a normal GitHub way. You can go and open up the issue, open up the request, and we'll address that. We'll talk to you, and feel free to leave your contact details, and we'll be able to discuss anything you want to say. Okay, and again, we have certain paradigm in mind, but the primary goal for us is to hear what people want and why, and make it usable.
Very good. I just put the link in the YouTube chat, so folks can check that out. We'll put that in the description once the video is uploaded as well. As someone who's been working in cybersecurity for quite a while, what were the biggest, I guess we could say, surprises for you in the process of building Kubescape?
Well, to be honest, the biggest surprise was how fast it was growing. but that aside, yeah. I think seriously though, I think that I've developed code for many years, and we have many young people in the company, and we started to talk about Kubescape. There was a discussion like what we develop and what we reuse, how we use other open sources, how we use OPA, how can we leverage existing pieces and build this tool fast. You asked before how we build it so fast, okay? And that's really biggest thanks goes to our youngsters who actually brought this idea and integrated all of these pieces very fast and make it work.
Wow. Okay. That's good. It's also good to see as well, too, the generational gaps and seeing things. And also what some people are saying as well, too, talking about what does it mean to be Kubernetes native, perhaps if not dealing with some legacy systems, it gives you a different vision. So it's very interesting that you brought that up. One thing before we finish, Leonid, could you stop sharing your screen really quickly so I can share mine?
Of course.
Lovely. So while we were talking, in our community, we have a tradition where we have an artist who's creating a graphic recording, a depiction of what's being mentioned. Let me know when you can see my screen. I think you should be able to see it. Good. So we have quite a few. We have quite a different few different things going on. We covered a lot of different things, but I think it was a very, very comprehensive review of diagnosing, the problem, seeing what kind of approach needs to be taken, and then the approach that was taken by ARMO CTO of interacting directly with those DevOps folks and seeing, the kind of challenges that we're having leads you to Kubescape, then further out through the demos that you showed us. Very, very good. And like I said, we got some really good comments in the chat. So I would love to have you back for a panel at some point about data security, because I do think Kubernetes presents very unique security challenges that I feel like security often is not taken seriously enough from the very beginning, and only becomes something serious when there's a problem and ransomware and having to pay lots of money and things like that. So I really think this is something that we as a community need to be proactive about. So I want to thank you for your time. I also want to thank Jonathan for reaching out, establishing the context so we could get this going in such a short period of time. And like I said, for everyone who is attending, you got the links to Kubescape. So check out the GitHub repo. Easy way to start interacting with the folks at ARMO. Leonid, thank you very much for your time today.
Thank you, everybody. And thank you, of course.
Have a great day.